Hey guys, Andre from High Performance Academy. Welcome along to this week's webinar. Now today we're going to be talking about a topic that I hear a lot of confusion about. This is the topic of compressor surge. So we'll find out what that actually means and how it can possibly damage your turbocharger. We'll look at the situations under which compressor surge can occur. And we'll talk about the solutions, how we can avoid compressor surge in the first place and how we can deal with it. Before we get into that though, there are a few things that I just want to touch on. Now, we have been building our Ghetto Build Subaru FA20 engine over the last few weeks. So if you've been joining us for our regular members webinars, then you will have heard me talk about the Ghetto Build. Now, a few people have hit us up about the terminology there, the fact that we've called it a Ghetto Build. And this is just a bit of a tongue-in-cheek take on the fact that what we're trying to do here is build a low-budget FA20 where we are only really addressing the major weakness that we've found to this point, which is the connecting rods. Now, a lot of people understandably have said, well, if you're going to go to the trouble of building an engine, why don't you go the whole hog? Well, the reality is that we are also building a full house engine that's going to be going into this car at a later point. So we've kind of got both of our bases covered here. We've got our low budget Ghetto build where we've only replaced the rods. We've got a high-end build where we've done pistons, we've done rods, but we've done a little bit more than just that. And this is one of the first things I want to talk about today. So if we head across to my laptop screen, this is a shot of the top of one of the halves of our FA20 block. Now what we've got here, as we can see, this is what is referred to as an open deck engine block design. And it's pretty common. Basically, it makes it much easier for the manufacturer to cast the block. And what we can see is we've got this water jacket that essentially runs the whole way around the outside of the block. And we can see that the sleeves or cylinders themselves are completely disconnected at the top of the block from the outside of the block. And in particular, we can see around the outside of the block, this is where our head bolts or head studs as we're swapping to, that's where those bolt down. In stock form, nothing particularly wrong with this, and as I've said, this is a cheap option from a manufacturing perspective. It makes it much easier for them to manufacture the block, so you can see why they go with this. What we do see problems with in basically any open deck block, alloy block design, is that particularly when we start increasing the cylinder pressure, because the sleeves or cylinders aren't connected or joined to the outside of the block, this gives them potential to move around quite a lot. So in extreme circumstances, this can result in the blocks, or the sleeves I should say, actually splitting or cracking. Obviously not something we want to happen. Even at lower extremes than that though, we may start getting problems with essentially the sleeves and cylinders do tend to walk around and move a little bit under high boost pressure, and this can result in problems with head gasket integrity. So this is a problem, as I've said, common with alloy open deck blocks. This really goes across the entire range of Subaru engines. So the solution we've gone to, nothing particularly unique about this, but I just wanted to talk about what we've done here. This is quite common practice. What we've done is performed what's referred to as closed decking. So it's a little hard to see because it's nicely fitted into place here, but Zach, our old employee, before he left, he was lucky enough to actually have his own CNC mill in his garage at home. So what he did was he machined up this deck plate, which we can kind of sort of get the idea of here. And this is just a very gentle press fit into the top of the FA20 block. So the block is also machined to accept this. Basically, the CNC program does both the block as well as the deck plate that fits in there. And it only requires a very, very slight interference fit there. Once that's all pressed into place, then this is delivered to our engine machinist, and that allows them to then deck the surface of the block back down smooth. And so the reality there, or the advantage I should say there, is once that's all in place, obviously we've now got a nice solid connection between the cylinders or the sleeves on the inside of the block and the outside of the block. This aids the block rigidity. It's going to give less chance for our cylinders to move around under high boost pressure. And the aim here, although obviously we haven't tested this particular one right now, the aim is that this engine should be much more reliable under a high boost application. That being said, we're probably still not really going to push this FA20 to the point where we're really going to be able to truly test this, but it's something that we wanted to do just as an experiment to see how this all worked out and give us some first-hand experience with that machining process and closed decking. So again, this is something you're going to see commonly applied, particularly to Subaru engines. Now the other option, the other extreme here, if you want to achieve a similar aim, is to completely machine out the factory liner. So if we just head back across to my first picture here, what we would have is a quality engine machinist essentially mill out the entire factory sleeve there right down into the bottom of the block, and then fit something like a Darton ductile iron sleeve, and using Ductile's MID sleeve technology, this essentially locates in the top of the bore as well. So this achieves two aims. First of all, we're going to end up with a much thicker sleeve, and because it's Darton's ductile iron, this is a little bit more flexible than a standard factory sleeve, so much less susceptibility to cracking under very high boost pressures. Because the top of the MID sleeve also locates on the outside of the block, kind of achieves that same aim of locking everything together to the outside of the block, giving that aided rigidity. Now, that's all well and good, but one of the common complaints or common problems we hear out there in the industry with sleeved blocks is that if the machining is not 100% perfect, then we do end up with risking the introduction of problems with the actual sleeves dropping in operation. Now, when that happens, we end up with the head gasket leaking, and basically we've got created one of the problems that we're trying to avoid. So when we're looking at the options of sleeving a block, yes, at very high power levels we may have no option, but in the interim a lot of people I see step into sleeve blocks when perhaps they don't need to, and again it is an expensive process, and if it isn't done correctly you can end up introducing more problems than you're actually trying to solve. Now I'll point out here that if you are going to be sleeving a block, you do need to be very careful with the machinist you choose, and that's not to say that no machinist can do this task, but it does, as I've kind of alluded to, it does need to be done very, very carefully here. And we had the opportunity to discuss this with one of the techs from Darton at PRI last year, and essentially he's suggested that to get this job done, the accuracy and the tolerances that is required really needs to be done on a CNC mill. And at least in our part of the world, there's still not too many engine machine shops that have access to that sort of equipment. So just keep that in mind there. And one other thing I just wanted to talk about while we are on the FA20 topic here is our piston choice. So we are running a set of JE forged pistons for this engine, and they are made from a 2618 alloy. Now the problem with that particular alloy that they're using for that forging is that it is incredibly strong, but because of its properties it does tend to expand a lot more as it heats up compared to a factory cast piston. Not unusual, this is a problem we see with all 2618 forged pistons. So we pay for that extra strength and the extra sort of flexibility, I guess is probably actually a pretty poor way of putting it, but that's essentially what we're getting with that 2618 because it does expand more. The problem with this is we need to allow for additional piston to cylinder wall clearance when we are machining the block to suit those pistons. Now, this particular piston is an older design from JE, one of their first for the Subaru FA20, and hopefully you can see here, we've got on the skirt here their friction reducing coating. Again, nothing particularly unusual with that. Now more recently, and I say recently, it's probably actually not that new. I think it came out perhaps somewhere around about the middle of last year. They introduced a new skirt coating. They call it their perfect skirt. So I've got one of the pistons that is going into our new engine here. This is essentially exactly the same forging, exactly the same alloy has been used, but it has their perfect skirt coating. So the advantage with that perfect skirt coating is it's actually designed to sort of wear in and take up some of that additional clearance between the piston and the cylinder wall. What you may be able to see, let's just jump across to our overhead camera here so we can get a better shot of this. You can see on that overhead camera there is a little window in that skirt coating, and this is quite important because when we are measuring the piston skirt diameter. We're going to need to use a blade micrometer to measure across those 2 points, and the reason we're doing this is it makes sure that we're not going to be affected by the thickness of that skirt coating. So we've still got what we would consider to be maybe a reasonably traditional piston to cylinder wall clearance in terms of the actual alloy of the piston, but then we've got that piston skirt coating that sort of helps take up some of that clearance, but we're not going to have danger of the piston actually seizing in operation. Upshot of all of this is we can get a forged piston that's going to run with effectively tighter piston to cylinder wall clearances. It's going to be nice and quiet in our bores, particularly when the engine is cold and is warming up, but we're going to have all of those advantages of a high quality 2618 forged piston. So we'll be looking forward to getting that engine up and running and seeing what it can do, putting it through its paces, hopefully in the not too distant future. Now, another product I just want to mention here, and this isn't actually a sales pitch, it's a product that I actually spotted a few weeks back, and it was brought to our attention by one of the members on our forum, and I sort of did a bit of research into the product, and it really did look like it was quite interesting. So we got sent one from AEM so we can take a look at it. So this is one of their X series wideband gauges. So nothing particularly unique about the gauge itself. It is just a wideband air-fuel ratio gauge, pretty typical tuning tool required for just about any tuning job. It uses the Bosch LSU 4.9 lambda sensor, which is pretty much being used by every wideband manufacturer, wideband controller now. So at this point, nothing particularly unique about that sensor. The part that kind of caught my attention that I really liked is the fact that this gauge, as well as being able to output the air-fuel ratio data via an analog 0 to 5 volt output, it also does something that, at least to my knowledge, is pretty unique. It outputs that information via CAN as well. So this is where the tricky bit comes in. It comes with this little OBD2 pass-through adapter. So this can go to the OBD2 port on your late model car, and what it does is it transmits that data on an address that you can then decode inside of a laptop scanner software. So the example that I'll give you right here, how we're going to be testing it and using it to start with, is with the HP Tuner's VCM suite or VCM scanner software. I know that a lot of people do have trouble getting wideband air-fuel ratio data straight into their scanner, and I've been in exactly the same boat, particularly on the older MPVI-1 interface. Initially what I was doing was using an analog voltage output from my Innovate LM2 wideband air-fuel ratio meter, and that goes to the side of the MPVI-1 interface from HP Tuners. The problem with this, and this really comes into being a problem no matter what you're outputting a 0 to 5 volt air-fuel ratio data into, is that the information is very, very sensitive to potential ground offsets. So what I mean by this is, depending how you wire it, it can be very easy to get a ground offset that essentially makes the data that you're seeing on your laptop or in your ECU complete rubbish. So those who have followed us for a while will know that I'm a huge advocate for CAN-based wideband controllers. When that data is sent via CAN, the integrity of the data is guaranteed. This means that no matter what we're decoding it in, whether that's an aftermarket ECU or whether in this case we're using it in a scanner for reflashing, we can guarantee that the data, the air-fuel ratio that we see, is exactly what the controller is outputting. So no chance of getting misled by ground offsets. So again, very new. It has only just arrived, well, new to us I should say. It has only just arrived across our workbench last week. So looking forward to getting stuck into that with our Holden Commodore and also our Chevy Duramax, and just seeing exactly how well that works. And I think we'll probably be including one of those as a giveaway in the not too distant future. All right, bear with me for a second. I'll just change back over to my laptop. Now, I'll just jump across to my laptop screen. I just want to quickly talk about this. And again, this is just a common occurrence. We're posting information up on our Instagram account. So if you aren't following us on Instagram, jump over and make sure you give us a follow. We try and post some really interesting information at least 5 or 6 times a week. So our account there is HPA 101. And the photo that we've got here, this is actually a car that we tuned a couple of years back now. And it's a Toyota 86 endurance car that's fitted with a 3-litre Synergy V8. So this is actually a New Zealand designed V8 V8 engine that uses a bespoke CNC machined aluminium crankcase and block, bespoke crankshaft, and it's topped with a pair of Kawasaki ZX12R cylinder heads. So stock form, this is a 2.4 litre engine. This one was stroked out to 3 litres, made around about 500 horsepower, naturally aspirated, which isn't bad from 3 litres, revving to about 11,500 RPM. Now the interesting part from our perspective here is these trumpets, which is what we're talking about in our Instagram post. And it's quite common to see on engines fitted with individual throttle bodies the use of an intake trumpet. And this is another tool in the tuner's arsenal. What we can find is by adjusting the length of the trumpet, we can affect the shape of the engine's power curve, where it makes peak power, and obviously that can have an effect on the maximum power as well. Traditionally, we would normally expect to see all of those intake runners exactly the same length though. And it was quite interesting to see this approach here, and I got the opportunity to talk to Simon from Synergy about why exactly they do this. And the reason they do this is that it creates a slight difference between the power curves of the 4 cylinders at the front with the long runners, the 4 cylinders at the rear with the short runners. And what this does is it tends to tame down the peaky nature of the torque curve on these Synergy V8s. That makes the engine a little bit more drivable, a little bit more forgiving, and a little bit smoother in that torque production, which again just aids the driver's ability to control the engine. So interesting take on there. Obviously the next question is, if we are doing something like this to affect the airflow into individual cylinders, we're going to end up with slight differences in the engine's volumetric efficiency between those 4 cylinders with the long intake runners and the 4 cylinders with the short runners. Absolutely, that is definitely a situation we're going to face. So how we deal with this: in the perfect world, we would run individual cylinder lambda sensors, and that would allow us to map the individual cylinders, making sure that our fueling is accurate across all 8 cylinders. In the real world, depending on how highly strung the engine is, often, first of all, that may not be an option, but often it's actually not as big a deal as some may think. And when we're looking at a lambda sensor fitted to the exhaust, clearly we are getting the average of the 4 cylinders, in this case a V8. We're getting an average of each bank with 2 lambda sensors fitted, 1 to each bank of cylinders. So what that gives us in this example, we've got on each bank of cylinders 2 long runners, 2 short runners. So what we might end up with is a situation where the 2 of the cylinders may be running slightly lean, 2 of the cylinders may be running slightly rich, and we tend to get an overall lambda value that's still kind of on our ballpark. So it's an important aspect of just understanding what that data is showing us. We may need to manipulate our air-fuel ratio targets slightly accordingly, unless we're dealing with a very highly strung engine where we're right on the lean limit that the engine's going to be able to run at safely. This generally is less of a concern than most people would think. Right, we'll head across to our YouTube channel, another of our social medias that you definitely should be following if you aren't already. And the video that we've just released today is one that we shot while we were at TX2K a few months back. And this is a car that we've followed pretty closely for a fair while. Cody from Cody Phillips Racing, probably one of the cleanest Supras that I've personally seen, and it was pretty fitting that he actually managed to run a couple of PBs at this particular event. So we get to find out what makes that engine tick, in particular the fact that he's near the 2,000 horsepower mark but is still on a factory cast iron block, and that's getting pretty unusual these days. We're seeing more and more people switch across to the billet blocks. They're becoming more available and obviously coming down in price as well. So we get a little bit of insight into the pros and cons of cast iron versus billet alloy, and we also get into the electronics package there that Cody's got fitted to that car, in particular some of the things he's doing with the Motec M150 as well as the power distribution modules fitted to that car. So if you want to learn a little bit more, head over to our YouTube channel, make sure you check out that video and also subscribe. That'll keep you up to date with all of our latest video releases. Lastly, before we get stuck into our webinar, We are running another one of our giveaways. We are giving away a Fueltech FT600 ECU. We are also including with the FT600 ECU our full suite of tuning packages, so you're going to know exactly how to set this up and get your car running on it. That'll include our EFI tuning fundamentals, understanding air fuel ratio, and practical standalone tuning course. Now, I have talked about this ECU a couple of times in the past, but for those who are a little bit new to this ECU, it is quite unique in that it's not only an ECU, it's also a driver display. So you can mount it in the cabin somewhere within eyesight of the driver, and it's going to basically double up as a driver display and logging center. And one of the unique features about this as well is it is touchscreen controllable. Now, you're probably not going to want to tune your entire engine, every single cell from the touchscreen. That's not going to be too sensible, but the ability to make small, quick adjustments from the driver's seat without the need for a laptop can be really beneficial, particularly when you are in the staging lanes or ready to go out on the track and maybe conditions change. So if you want to get yourself into the draw for that package, make sure you click on the link I'll get Ryan to drop into the comments and get yourself into the draw. I don't think that's got too long left to run either, so don't miss out. There's also a bunch of opportunities there. You can follow some simple instructions and get yourself a few more entries into that draw to bump up your odds. All right, thanks for watching there. Give us a few seconds and we'll get started with today's webinar.